We're going to begin Chapter 21, Mechanisms, with an exploration of the Claisen rearrangements. So we got to be careful with Mr. Claisen, Dr. Claisen. He's got two reactions now. Yeah, it's clearly we broke a group off and put it somewhere else. It looks like it ended up down here, huh? Yeah, that's interesting. The electrons are going to flow like they're resonating in benzene during that mechanism. And I'm going to ask you, do you remember any other mechanism where that happened? You're going to say, yes, I do. You're going to say beta decarboxylation when we get there. But the first thing we're doing is simple acid base in step one. pKeq equals -6. And then an SN2 reaction. That's it. We're setting up a Claisen rearrangement from phenol, which is pretty cheap. And then making a bond on benzene, that's valuable stuff. So it's a very valuable process we're doing here. Putting a new group on a benzene, not easy to do. Yet this affords us a way that is fairly easy to do. Acid base. You got a lone pair on the O. So some of you are looking at your tests and saying, sometimes he takes a point off if I forget that charge, and sometimes he doesn't. I'll explain myself. I'll have a student do this on the test. They'll leave the K there, and they'll put the lone pair on there. I don't mind. You can do that. You can use that lone pair for the mechanism. But on the same exam, some students did that, and then another example, they did this. They crossed off the spectator, put the lone pair, and they did not acknowledge the spectator took a charge with it. So let's cross it off with a different color. We cross it off. Now you got to put the minus. So am I clear? Yeah. You can just put the lone pair if you don't cross off the spectator. And I'll just pretend the spectator's just hanging around for the ride. But if you cross it off, I need to see the lone pair and the minus. Okay. Acid base. You made phenoxide. Phenoxide, strong nucleophile, plus H2O. pKeq equals -16. Wasn't asked, -6. Wasn't asked for. But, you know, there it is. 10 for a phenol, 16 for water. S2-bromohexene. That wasn't enough information there. Sneak the 1 in there for me. Sorry about that. S3-bromo. 1 hexene. So you got your 1. 1, 2, 3, 4, 5, 6. 3 bromo. Which one has the bromo? Right there. There it is. S. Backside attack, leaving group leaves. That's it. Setting up a Claisen is easy, speezy. Step 2. And backside attack on an S stereocenter gives what stereocenter? R. So is that H on a wedge or a dash here? It's got to be a wedge. And pick an adjacent bond for a dash. There you go. There it is. Nice. So it used to be S. Just a reminder, it used to be S. And when you're done, it's R. This was an SN2. The Claisen, as promised, the arrows look just like benzene resonating. So you know that's a favorable situation with the 6 pi electrons moving around in a circle. I know some of them didn't start as pi, did they? But as this bond's breaking, it's going into a pi bond. As these sigma electrons break, they go into a p orbital, so they can make a pi with the carbonyl, which you're about to draw. And here it is. Double bond there, carbonyl here. New bond here, exciting stuff. Goes to CH2, goes to C, goes to C double C, CH2, CH2, CH3. And I gotta remind you, this thing's not aromatic anymore. That's why this step is the one that requires all of the, what's that I just put over that arrow? Heat. Yeah. You're taking something that was stabilized by aromaticity and you're destroying that. How do you know it's destroyed? This is sp3 down here. 1, you can't resonate with it. 2, in the ring, there's only 4 pi electrons. Don't count these, they're outside the ring. Don't do it. You got to be able to resonate in a circle, right? So you only have 4 pi electrons, and they're getting stuck here because they can't get past this point. sp3, it's like a dead end. It's like a wall. All right. So how do you get from there to here? If we're doing a tally, this might be the 15th time. Taking a carbonyl, making something that's now an enol. Oh yeah. 2, 3. Say it again. Nice. Only 3 seconds this time. I was about to start dancing. She said tautomerization in time to save you from watching the dancing. You should thank this woman. All right. There's no chemicals present here. There aren't any. Just this chemical we drew. That's the only chemical. So where's it going to get the H from for the O? Say it again. There is no acid. From itself. Oh, I think you're invoking the old intermol, aren't you? Yes, he was. So you're going to say the pi is going to grab the H, but you got to acknowledge it can't reach. So you write intermol over that one arrow, the one where it can't really reach. And there you go. And that is a tautomerization. And there you go. So when do you get a Claisen rearrangement? It's when you have a phenyl allyl ether is a Claisen rearrangement. That deserves a highlighter. Those circumstances provide an arrangement where the electrons can go around in a circle like this. We call that pericyclic, if you want to sound fancy. It's a pericyclic reaction, just like beta decarboxylation had the same 3 arrows going around in a circle. Pericyclic reaction called the Claisen rearrangement because you started with a phenyl allyl ether. And the greatest part is you made the sigma bond on the benzene. That was nice. And that's the end.